Okay, great. We can start now. Okay, so as you know, this is the third lecture in the ZI Learning, in the ad hoc module of the ZI Learning series being conducted by the by CodeChef and an academy. It's part of the wider ICO Learning series. Now, ZIO, as you know, is the first stage in the computing Olympiad and is a four-problem integer type exam, where every problem has three subparts. Now, the exam is based on algorithmic thinking and informatics-based intuition. And qualifiers get to then appear for the next stage, which is INOI. About me, I am a 12th grader from New Delhi. I cleared INMO and I'm also an APMO medalist. I cleared ZIO and ZCO last year, and as you know, this is the second module I'm teaching after the number theory module. I hope the lectures have been helpful to you and that you enjoyed them. Today, the plan is to cover a few ZIO problems that you recommend, that you all told me that were you found troublesome. We have I have three such problems, and we will be discussing those. Is that okay? Yes, of course. Isra, there's nothing. There's no problem in that. Okay. So the problems we plan to discuss today are ZI 2019-4, ZI 2018-2, and ZI 2017-3. So, as you know, the third lecture is based on solving ZI problems. So this is the first problem that we plan to discuss today. Have you seen this before? Okay. So, do you have any idea how to solve it? Okay, I'll explain the problem to some people first. You have an n by n grid. That's n square, n rows and n columns, and you have unit squares everywhere. Now, every cell you can write the number 1 or minus 1. Such a grid is now called a binary grid. Now, the row product of any row is defined to be the product of all elements. So, you just multiply the elements in that row and you call that value to be the row product. So there are, because there are n rows by definition, the n row products and similarly n column products are defined. We want exactly one of these to be minus 1 and the rest to be 1. So one column product should be minus 1 and one row product should be minus 1. So how many grids are there that satisfy this condition? Okay, so how do we go about this? Any ideas you have? I would prefer if today is interactive because it's just problem solving, and that's preferable if it's interactive. Uh, any ideas, anyone? Any at all? Okay. So the answer is this value. Hi. The answer is this value. So does this value suggest something to you? Like, can you guess how we could have this value? What things we could have multiplied and why would we have multiplied them? Hi, Abdullah. Any ideas? Okay. So see, we have n rows, right? These are n rows. And similarly n columns. Because these are n rows and n columns, this seems to suggest that we are multiplying n into n somewhere. So remember that you're choosing minus 1 in one of these rows and minus 1 in one of the columns. So that's probably where the n square comes from, right? Because remember, only one column has the value minus 1 and only one row product has the value minus 1. So the number of ways of choosing one row is n choose 1, which is just n. Similarly, n choose 1 columns is n. Now, this is 2 to the n minus 1 whole square. So that seems to suggest if we fill some n minus 1 whole squares arbitrarily, we would have a fixed grade. It seems to suggest that. It doesn't necessarily imply it, but it seems to suggest it. So let's go by that logic now. Let's think in that way. So let's just first define our squares, where Cij is the square which is in ith row and jth column. We define the row product as Ri and Cj. Now there are n square ways to pick the row column pair which have product minus 1, so we have the n square term. Now we fill the cells Cij arbitrarily whenever max ij is less than m. What that's basically saying is, if this is our grid and this is like the last row and the last column, we leave this area for now, and the remaining n minus 1 whole square things, remember that every point there are n minus 1 whole square things here because n minus 1 into n minus 1, and in all of the squares are taking arbitrary values. So each of them has two options. So we have 2 to the n minus 1 whole square. Now, when we have filled this, let's start filling this area first. Now observe that when we have decided that this product is 1, this product is minus 1, this product is 1, and so on, we have fixed values here because we have got some product here and only one desirable value works. Only 1 could work or only minus 1 could work here. So we have no option with these. Similarly, we have no option with these. Now, the main thing is, what do we do here? So, now the only square we are left is Cn comma n. So we choose the value so that this row is satisfied whatever the condition is. And we claim that if we satisfy this rule and we follow the rule as before, even this column is satisfied as the product we wanted. So how could we show that? That even this would be satisfied? Any guesses? Any guess at all? Uh, could anyone respond? Yes, okay. So could you please guess why this works? Okay, the important thing to notice is the product of the values row products, the product of all row products is same as the product of all the values of all cells. So it is also same as the product of all column products. Does this make sense? Yeah. So if sum, because this quantity and this quantity are equal, so the number of minus ones here we know is minus 1. So this value we know is minus 1. So either there are 1 minus ones here or more than 3, greater than equal to 3 minus ones. But by our choice, we know that in this much, in these column products, there is maximum 1 minus 1 because we have chosen it that way. Either the minus 1 is on this column or the minus 1, there's 1 minus 1 here. So there can be just maximum uh, 1 minus 1 in this much whole thing because 2 doesn't work because we need an odd number, so which is at least 3. So there is exactly 1 minus 1 and that's what we wanted. So this construction works. So that's the answer and that's how we solve it. So the main motivation here was you should realize that when you're considering the row product, the last thing kind of does not matter. I mean, whatever you fill here will not matter because only last thing is the deciding factor. So you can pick this much arbitrarily. So if you fill this much arbitrarily, then you are fixed with this much and for this much. Then it's kind of, you can guess that this should also be fixed. Now you can easily, for proving that, it's a very common idea to consider this value, how they compare with each other, row products and column products. And now, because you wanted the n squared thing, you have any option as you want, you get the n squared term. That's kind of all there is to it. Is this much clear? Okay, great. Others? Is it fine for others? Okay, there seems to be some confusion. Could you explain what the confusion is? Oh wow, a lot of you are confused. Could you please explain what the confusion is? Anyone? It becomes hard for me to explain if you don't tell me what the confusion is. Could you please explain? Okay, since no one is reacting, I cannot go over the whole thing again. Unless you tell me what the issues, I'll move on. Okay, moving on. Now the next problem we have is ZIO 2018-2. So now, the problem statement is very simple. The problem says that you have some boxes, some balls of some colors. There are 12 colors. There are 8, in the first case, there are 8 balls of the first color, 22 balls of the second color, and so on. And you have 11 boxes. Every box can have at most 10 balls. Now, you want to arrange them in some way such that the boxes which have more than one color are minimum. So, what is the minimum number of such boxes you will have which have more than one color? That's the entire problem. Here you have 13 boxes, and here again you have 13 boxes and some different color arrangements. Is this okay? Uh, is the problem statement fine? Yes, okay, great. So we'll now try to pick the maximum number of boxes which can have exactly one color or at most one color. So, and then we're subtracting from the total number of boxes, and that gives us the same thing. So what can we do now? So observe that if we always fill a box fully, if it's impure, impure means that it has more than one color. We'll try to fill any box which is impure with as many balls as we can because it does not harm. I don't see how you'll brute force 13 things and how you prove that it's your thing is accurate. The greedy algorithm here works, but yeah, the greedy algorithm here works, but it's not trivial to see that why it works. Similarly, for every color, we can assume that maximum one pure box is not completely full because otherwise we can take the balls from one box and put them in the other ones. So we can easily assume these things. Now comes the main part. We start by analyzing. Okay, so we can always pick the largest element. So we see what the largest element is. The largest the largest element means whatever color has the largest number of balls, and we fill a box as much as we can and repeat for as long as we can. Sometimes we won't be able to fill a box. Sometimes the issue will be that we don't have enough boxes for the remaining things after we do this. So everything at that point will have to be impure. So for this, we can write this algorithm. Do you see what this algorithm says? Do you understand what this algorithm is saying? The algorithm says that you start with some value 0, that the number of the number of pure boxes is 0. Now, whenever the sum of all terms is greater, sorry, this should be less than equal to, and this should be less than equal to. My bad. Anyway, so while the sum of things is less than 10b, we do this. We consider the maximum term. The maximum term may be more than 10. So we only take the maximum part if it's less than 10, otherwise we just take 10 balls. We say that there are 5 balls. Now, if the sum is still less than equal to the sum of the remaining balls, we can create this new box. So S increases by 1 and we are left with the problem with B minus 1 boxes and AI decreased by I. In the case this is not true, then when we go to this, there will be 0 ways to do it because the loop will break. So we'll get S goes to 0. So we get our answer with this algorithm, and this algorithm works. So let's now try to implement it. Is the algorithm fine? Do you understand what the algorithm is doing? It's hard to interact this way. Could someone please try to type if they can, if they understand, other than Abhinav, because he's the only one who's responding right now. Okay, okay, yes, some new people have joined. I'll explain it to them for now. So the problem is we have some box, we are given a number of boxes and some set of colors. We have 12 colors, and every color there is some balls we have. We want to put these balls in these boxes such that we minimize the number of boxes which have balls of more than one color. So what is the minimum such number of boxes we can have? We are calling such boxes impure, and the ones which have all of one color as pure. So now we'll try instead to pick the maximum number of pure boxes and then subtract from the total. So what we do now is whenever there are there are enough balls to place, there are enough boxes to place the balls, we consider the maximum term in the color set, the color with the maximum number of balls. Now the balls there are of this color and 10, because we know box can store more than 10 balls. So we try to take this value, remove it, and then check if we can still do the thing. If we can still do it, then we get one extra pure box. Otherwise, we won't be able to do it, and when this thing happens, the loop will break. And if this is still true, the loop won't break and we can continue. And this algorithm works. Could anyone explain what the issue is instead of just giving me emojis? That's quite unhelpful. If people continue to react with emojis without explaining the issue, I'll have to move on. Okay, so with this algorithm, we can now implement it. Now see, here are values. We have the set of values as 8, 22, 4, 4, 9, 8, 7, 6. So now see, first we'll pick the value 22, then which becomes 12, and we get one pure box. Now the maximum value is 18. This goes to 8, and we get another pure box. And then we pick 9, and but this time we decrease by 9. This becomes 0, and we keep going. Now we pick 8, 8, 8, and this process continues. In the end, so we pick A2, A6, A2, A5, A1, A6, A7, and we keep going. And after these steps, we have this as the structure, and we are left with B equal 5. Now, see that we have A8 as the maximum term. So we can pick A8. But as soon as we pick A8, the process will have to terminate, because we won't be able, the maximum term now is not pickable. We can't give it a separate box. So here we already had 7 pure boxes and we get another one. So there are total 8 pure boxes. And because there were total 11 boxes, so our answer is 11 minus 8 equals 3. So we have at least 3 impure boxes, and that's our answer. The same process will now in the second part give us 2 impure boxes and 4 impure boxes. Is this fine? Also, if you have an issue, please don't just react with an emoji, explain it. You can take 2 minutes to digest the algorithm, and then we can move on. Anyone? If it's fine, you can still tell me. If it's not fine, then you can still tell me. Okay. You can still take another minute. Okay, I'll once check the YouTube chat if there are any issues there. Okay, great. Okay, I'm checking the YouTube chat now. There are no issues there, and we'll move on. Okay, great. Thanks, Abhinav. Now we have the last problem I had planned for today. After that, if you have any other problems that you want me to check out, I can probably do that if we have enough time. So you have a group of n people who want to play hide and seek. In a single round, there is one seeker and n minus one hiders. Children like to hide, which is weird because the people I know like to seek. But okay, here children like to hide and not seek. And each child has her own idea of how many times she would like to hide. So everyone wants to hide at least some given number of times. So you'll be given a number for each child I, a number hi, that tells how many rounds they want to be at least how many rounds they want to be the hider. And they'll only be satisfied if they get to hide in that many rounds. So we want to find out at least how many rounds we will need to have so that everyone is satisfied. Determine the minimum number of rounds for the following three cases. So how will you do this? Any ideas? Let's consider this case for now. Also, you can ask things on YouTube. I have the chat open now and I can check it. Now you can't brute force everything. This is absurd to brute force. I don't know how you have the stamina to do it. I wouldn't be able to brute force it. Come on, brute force. And you wouldn't be able to do it if the contest was not integer type. Then, otherwise, if the contest was a proper coding contest, then the time complexity of a brute force would be too bad. The current time complexity is just O of n. The YouTube link should be available. I don't know how to share it right now. But it's kind of irrelevant. You can find the content on Unacademy because YouTube stream is just screen sharing of the Unacademy link. The content here would be clearer. Okay. So any ideas for this? Anyone? Anything? Okay. Nobody seems to be reacting. So let's see what we could have. Let's assume for now that there are k rounds. Now a child can be a seeker in maximum k minus hi rounds because they want to be the hider in hi rounds. I'm sorry, whosoever is reacting with confused emojis, please stop. Uh, Now let the person be a seeker in k can be a seeker in maximum k minus hi rounds. So, but observe, for this to happen, if there are k rounds, k needs to be at least hi, because you can't be seeker in negative number of rounds, and if there are less number of rounds than the number of times they want to hide, this can't happen. So we need that k greater than equal to hi. So k would have to be greater than the maximum of all terms in h. So also we will need to have that the number of rounds k is less than equal to the sum of maximum number of times everyone can be a seeker. We'll need to have this. Thus, we get that the sum of hi is less than n minus 1 into k. So k would have to be at least the ceiling. Okay, I'm sorry, I don't know how hi is missing here, but it is. uh, k has to be at least the sum of hi upon n minus 1 and float. Thus we get that k, again hi is missing. Very sorry for this. Sum hi. K is at least this amount, and k we know is at least this amount as well. So we need k to be at least the maximum of these two things. And when we have the maximum, you can see that all conditions are satisfied, because we can make the seekers according such that everyone has enough chances to be a hider. And that's the computation we just need to do now. Again, this is hi. Sorry, I just copy pasted it and I forgot to put hi. Very sorry. Okay, so we want the maximum of, because the terms were 6, 13, 9, 5, 15, 8, and 9. Because 15 is the maximum of these terms, and we want the maximum of this floor. So that becomes the maximum of 11 and 15, because this sums to 65, which is just 15. So our answer is 15 here. We can do the same thing and we'll get maximum as 10 and 9 is 10. And last case, I'll leave for you to calculate. So whoever does it can type the answer in the chat. Here are the values. Can someone do it right now? This part. Please try. Uh, Anyone? Any ideas? Considering the fact that no one is even acknowledging, I'll have to move on. We'll get the sum of the floor of the ceiling of these sum upon n minus 1 as 145, and the maximum term is clearly 140. So our answer becomes maximum of 145 and 140, which is 145. And that's our final answer. Now, this is all we had planned for today. So if there are any other problems that you would want me to discuss, I can do that right now. ZIR 2018-4. Let me find the problem. Could you in fact post the problem statement in the chat? It may take me some time to find it otherwise. The Manhattan distance problem was covered in the lecture by Neelav. You can check that out. Okay, ZIR 2018-4 has also been discussed actually. Uh, no, I discussed it in one of the sessions I conducted, but because there's no way to do this other than brute force. Sadly, the only way to do this is brute force. So I don't think there's really much I can do to help you in this. Anything else if you want, something that has not been done yet. Uh, Anything? Okay. Then Sid, I'll wait for another minute or so and then move on if there's nothing. Let F N be the child. Okay, this is a problem from one of the earliest sets. So Lana has shared it on the YouTube chat. I'll I'll see it to it. Ah, okay. Yeah, I remember it. So there are two conditions that f of 2n is equal to 2f of n and f2n plus 1 and we have f of 1 equal 1. The problem you are asking me to do for 1 and 5 is actually not that hard because for 1 and 5 you can just calculate the values. F of 1 equal 1, f of 2 equal to f of 1, so it's 1 equal to f of 3 equal 1, f of 4 equal 4, and f of 5 equal to 3. So in the case you are telling me to do, this is just this and this. So our answer becomes 1 plus 3, which is 4. But the interesting part is the general case. What happens when the thing we are doing is general? In fact, if you now try to continue this, you'll notice something very interesting. F of 6 is actually 2 and f of 7 is 1, which is interesting because the pattern seems to be coming this way. You have 1, then you go to a power of 2, 2 and then again 1. Then you have 4, 3, 2, 1. So at powers of 2, you seem to be going to the power of 2. Now f of 8 equal 8. Enough. So going to powers of 2 and then just decreasing all the way down till you reach 1 and then going to the next power. So this seems to be a very interesting thing that's happening. And now our natural instinct is to see how to prove it. So let's consider this set. The things between 2 to the n to less than 2 to the n plus 1. So from here to here, from this set. Now let's assume we have proved this for some power of 2, that this result follows till 7. Now we want to prove it for 8 to 15. How do we do that? Because 8 is the double of 4. The next thing comes as the power of 2 that's required. But now notice that whenever we move forward, our term actually decreases by 1. Because 2 f of 9 is 2 into f of 4 minus 1. But 2 into f of 4 is f of 8. So 2 f of n is f of 2n. So in fact, every odd term is one subtracted from the previous number. So you decrease by 1. But notice that when you're going even to an even number, you're changing by a difference of 2. But that's the different double of this difference, which is 1. And that's what we wanted. So you get the pattern forever. And then you can easily calculate the positions that comes by using the binary form. You can even write it at even this point as if the number f of n equals to n this term is actually f of n. And then you can do it in the general way. Okay, great. I'm ignoring the confused emojis, but because no one is actually explaining what the issue is. Okay. Uh, Anything else? Could you give me the problem? I don't remember problems as such. Again, I've never coded on ZI and code forces, and I don't even know how the rating system works. I don't know how code forces rating systems works and what a rating is. Stable matching problem is not really relevant here. It, you can ignore it for now. It's not really complicated, but it's unnecessary. Okay, there doesn't seem to be anything else, so we'll move on. So now, as you know that you have only 6 days to ZIO as it is on 19th, and okay, this is my personal opinion, but I don't think you should be at least in the last day before the exam or the 2 days before the exam, you shouldn't be doing much. You should relax. Even this week, you should relax your schedule a bit. And but other than that, if for practice, I think previous year questions are the best thing at this point. And doing new theory and other things won't be really helpful at 6 days prior to the exam. I mean, you can keep doing problems for fun at even the last day, but remember, like, you shouldn't take any pressure or just do it for fun. Don't do it like I have to do it for the exam or anything. Also, just be careful for the exam. Just follow safety regulations. It's a bad time. Just respect it and go into the exam with a calm mindset and safety. I hope you do your best and you enjoy the test. All the best. Thanks for attending the lectures. Is there anything? Actually, I won't be going for the exam. I won't be appearing. Uh, the number is actually very varying, and I don't know what the exact numbers are. But I think about 100 to 150 students are selected from ZIO, and about 15,000 to 1,500 people write it. Why? This, yeah, nothing to, I can't really discuss it here. Anything else? Again, I'm not informed of those things. Uh, uh, yeah, but I do know about 1,400 people enrolled in the Unacademy course, so that may give you some sort of hint to the number of people. Okay, bye bye. Thanks for attending. Please fill the feedback form. It's linked and it's pinned in the chat. Please fill it. My Discord username is RG230403 with this tag. Vijay, you can use it, or you can just tag me as at the rate Rohan Goyal on the server. Vijay, you wanted this, so you can use it. Thank you. No problem. Uh, Bye, everyone. Thanks for joining.